Well, welcome everyone. Some colleagues I see, but also our sponsors and parents. Each semester, students are given a problem with various constraints, and it can be a kind of a catch as catch can. I mean, the problems can be varied from robotics to heat transfer to whatever. And they have to take this challenge and make something work on a budget and on time. And so this year, or this semester, Group 18 had to work on cooling a piece of sensitive equipment. We're grateful to Consumers Energy and to Stephanie Pierce. She's been a great sponsor and help to our team. And our team is going to introduce themselves to save me the embarrassment of mispronouncing names. So please, take it away.
Okay, yeah, so thank you all for coming. My name is Zac Seeds.
My name is Campion.
I'm Alec LeVasseur.
Paige Brechtelsbauer.
Jennett.
And we're going to show off our cooling system for Picaro's advanced methane detection technology. So just to give you a little bit of background, Consumers Energy is one of Michigan's biggest gas and electric utilities. They're actually Michigan's biggest gas utility, so they have thousands of miles of gas pipeline to make sure that they're transporting gas safely, there's no emissions. And so to help with that, they purchased 2 methane detection systems from Picaro. These go in the back of the vehicle, they run off vehicle power for the most part, and they're able to detect very small amounts of methane from very far away. But these systems, sometimes when the car is shut off and the Picaro system isn't, can overheat in the summer. And that causes a premature shutdown, which is, to get out of, it requires a pretty complex process, which leads to a lot of downtime. So we built a cooling system to try to prevent that process and prevent that downtime.
Alright, so like I said, in the summer is the main problem for us. So the sun's radiation will come through the window and then heat up the interior of the car and just make it excessively hot. You've all seen hot summer days and get into your car. So that's the issue that we're trying to get rid of. And like he said, once the system overheats, there's a few components inside of our system, chiefly named the warm box, hot box, and CPU, that once they get above a certain ambient temperature, they start to do an emergency shutdown process. And like you said, once that happens, it takes a long process to get that fixed. So that's basically what we're trying to fix here with our cooling system.
Okay, so the problem constraints, we can't attach it to the actual device itself. We can only attach it to the extruded aluminum or to the wood flooring. There is a finite usable area for design, which is the back of the car that has to fit within this area. And the system must be able to withstand Michigan potholes and God forbid car crashes.
Alright, so now we're going to go through some of our initial design ideas that we had for fixing this problem. So our first idea was kind of an over-engineered design of having an ice machine with a refrigerant cycle freezing water and then dumping it into a reservoir, and then having that reservoir feed into a heat exchanger, an air-water heat exchanger that will then cool down the system. And this is just a mess of things because if we're using the refrigerant cycle for freezing the water already, that would just kind of be meaningless to not use that to cool the system itself. So it's kind of just a mess of ideas right there.
The second design idea is the one we have now. It's where we have ice and water, which you manually add, for example, into our reservoir there every day. The reservoir keeps everything contained and cool to an extent. The cold water, when it turns on, will then circulate through the system and then come through the heat exchanger that is inside of this enclosure, trying to keep most of the cold in the box. And design idea 3 is an air conditioner. This would be like a typical refrigerant type that's in your car or your house. This would run on a battery which would charge when the vehicle's charging via the alternator. And then we would either have our own, like, build your own type of kit, like the RV kit we found, which comes with all the lines and the compressor, the condenser, the evaporator, and all that. And we'd assemble that. Or we'd buy a commercial system like the Zero Breeze Mark II, and that system uses a 24-volt power supply, which we could either use a battery or power ourselves. If we used use this idea, we would have to get rid of the heat somehow. So in the condenser, you would have to either have it outside the car or inside the car, either way if you're putting heat somewhere. And it would add a pressure difference if we use a zero breeze, because that comes right off of the device and then it blows into it. But if we use the build your own kit, we could actually have the evaporator inside of the control volume, so we could have all the air circulating inside of the control volume.
So in addition to whatever design you choose, we knew that we needed some added benefits to keep the car from heating up. That would make our system just a little bit more efficient. So one of these would be to add reflectors to the windows. They could even be branded, say Consumers Energy, serve as an advertisement and a way to keep the car from heating up as high as it normally does. And then the other is just making sure to crack the windows in the summer when you leave the vehicle, just so that we can enhance the convective heat transfer between the vehicle and the outside, so that there's less runaway temperature, it's closer to the outside ambient temperature.
An evaluation of options. When it came down to it, there was a lot of going back and forth of what we wanted to do. Ultimately, we chose design idea 2 because it is the simplest, it is the cheapest, and it is the safest. For example, the refrigerant idea, if we had to make it ourselves one, there's a possibility that we didn't make it right. We're not HVAC techs, we don't know exactly what we're doing with that stuff, and we don't want R134A or R12 coolant being loose in the car. As for expensiveness, like if we bought the zero breeze, that's really pricey, it's about $1,000. Same if we bought an ice maker and did all that stuff together, ice maker is about $400. For simplicity, this is also the most simple design, besides maybe putting the zero breeze on there, but again, there's those drawbacks with the safety and also the use effects.
Alright, so like you said, we went with design idea 2. So here we have our system here. We did change it a little bit. We moved the pump outside of the reservoir, so now it's in line, moving the mass flow into the heat exchanger with airflow coming from the box and staying inside of the box, cooling everything in there. And then we have it coming back into our ice water reservoir, which will be refilled by the technicians daily or whenever it is needed, if it's an extremely hot day, that kind of thing.
So the design idea 2, we also needed to verify the theory behind it to see if we could actually start prototyping the project itself. So we wanted to determine how much energy is entering the system through an enclosure, and then see how much energy we were removing via the heat exchanger. And so we had to do some calculations. And so the box will be sitting outside in free convection. There's no airflow when the car is off. And so first we had to determine the front, back, and side Rayleigh numbers depending on these constants for gravity, beta, the inverse film temperature. And so the characteristic length L for all the front, back, and sides are the same. So the Rayleigh number remained the same since all walls are the same height. And then this allowed us to plug into our Nusselt value equation with using the properties of the air. For the PR number, we determined a Nusselt value of 81.6. And then this allowed us to determine the convective current used, convective current of the outside air, which was the convective coefficient, which was 3.82 watts per meter squared Kelvin. These temperatures are based on a worst case scenario for pediatric report of pediatric safety in cars, and cars could reach up to 67 degrees Celsius. And we assumed that we wanted 27 degrees Celsius within the box. And for our surface value, we took the average of the two. And so we had to also determine the top, but the Rayleigh equation remains the same, but the characteristic length changes since it's a horizontal wall. And so we took the ratio of surface area to the perimeter and to that, then plugged it into the Rayleigh and plugged it into our equation for an upper surface of the cold plate, since this is a cooling system and the top surface would be cold actually, and we were able to determine a convective coefficient of 3.66. Now we have to do a thermal circuit, and since now we know the convective coefficient around the box, and we know the conductivity of each material that is made for the box, we can determine the top, front, back, and side heat flux using our circuit. And we can, once we determine that, we multiplied out the area of the entire box to get a total of 296 watts entering the system via the box. And we used an iterative process where we got a value of 36 degrees the set heat flux is the same throughout the box at certain thicknesses, and outside we're able to determine the outside surface temperature, and we iterated that 4 times using the values we got, and then reinserting them back in our equations, and we got a value of 36.8 degrees Celsius after 4 attempts, giving us a max heat entering of 326 watts. Now that we have the temperature of the wattage of air entering the system, we need to determine how much we can actually remove. So first we need to calculate the Reynolds number depending on the max velocity of the air crossing the heat exchanger. And so that is based on 3,000 CFM, which gave us a velocity of air of 10 meters per second, giving us a Reynolds number of 6,500. And then to calculate our Nusselt value, to calculate the convective coefficient, we need to determine the ratio of the length of between each row and the diameter, and that gave us about 2.2, and we approximated to 2 to give us, and then we also had to take the ratio of the distance between each pipe in the row over the diameter, and that gave us approximately 1.5, giving us the constants from this table to give us C1 is 0.4, and then it's 0.568. And then since we wanted a staggered orientation with 3 rows, they gave us our final constant of 0.82. And entering all the values we've got, along with the PR value for the air, the film temperature of air going through the heat exchanger, we got 52 for a Nusselt number and 45.74 for our convective coefficient. And lastly, we had to determine the convective coefficient of the water that is going through the pipes. And so we used, we need to calculate the Reynolds number depending on velocity of the water for the certain diameter of tube, and we had 330 gallons per hour entering the tubes, giving us a Reynolds number of 2.65 times 10 to the 4. And for internal turbulent flow for cooling, they gave us a Nusselt value of 171.6, allowing us to finally get our last needed value for convective coefficient of 10,250. And then finally, since we know the H for water, the thermal conductivity of copper, and the H of air, we were able to determine that the system is inserting 1,200 watts. But since the fan only covers approximately 1/2 of the area of the front of the radiator, we had to multiply that fraction into our system to get 563 watts of cooling, which gave us a net value of over 200 watts. And so we were able to use this to start prototyping.
Great, for the prototype build, while building it, we decided that we needed braces to be able to support structural integrity of the box. So we're going to go back and forth. We used fitting concealers for all mass flow lines. What we mean by that is we had to use Teflon tape and other things like that to seal the water lines. We also used some self-bonding tape and different fittings. For the air, we used basically a pool noodle for the bottom. We used some weather stripping for the sides, and in the back we have freezer curtains. We use particle board for the top and the sides because you don't need to see through those, and it's pretty good at thermally insulating. The plexiglass in the front so you can see through. The operators can look at the device and see what they need to see. And for the back, we use freezer curtains so that the wires can go through and it's more easily accessible and can slide out easier. Electrical design overview. We use a 12-volt battery to power the system, so it's not as dangerous as like 110. You don't want to get shocked by that. The pump and fan are in parallel, so then fuses and diodes to protect the circuit. So the fuses, we have 20 amp fuses on it because the pump and the fan are both about 10 amps and the wires are rated to about 30, so somewhere in the middle we chose the fuses. And we have flyback diodes on the pump and the fan because they produce an inductive load when they're shut off, and that increases the voltage like really high, and that can mark across the chip. And the MOSFETs and relays are used to switch on the fan and pump, which I'll talk about in the slide.
Okay, so this might look a little bit intimidating, but this is our electrical circuit that controls our system. So controlling 240 watt system with a small Arduino is not a trivial task. we decided to use MOSFETs, which Thomas mentioned on the other slide, which are just simple transistors that can act as switches when given an input signal. But the MOSFETs that we chose were spec'd for 15 amps, which we thought would be fine. But when we ran with these MOSFETs only, we were getting really high current spikes right at the beginning, which were just destroying the MOSFETs. So we had to add in larger solenoid-based relays that were then controlled by the MOSFETs. So these relays can handle 30 amps. They're really robust. Every time you run the system, we're sharing the load between both of the relays now. So the system runs fine. These are the flyback diodes that Thomas was mentioning. They make sure that when there is an inductive load, it allows it to cycle and dissipate. And then we have the fuses in there. The blue is anything coming into or out of the Arduino. The green is anything in our smaller 12-volt circuit, which just powers the relays. And then the black is our larger lead-acid 12-volt circuit. So from the last slide, you can see that there are inputs and outputs on the Arduino. I just want to explain each of those. So for inputs, we wanted to be able to read the temperature in the car to determine if there is overheating. And we also wanted to be able to determine if the car is on or off. Because if we know it's a hot day and we know the car just turned off, we may as well start heating right then to keep the runaway heating from happening. So we have a thermistor circuit that reads the temperature into the Arduino. And then we have a voltage divider, which takes the output from the car battery. It reads 13.5 volts when the car is on because it's running on the alternator, and it reads 12 volts when the car is off. So we use that to determine the on or off state of the car. And then from those states, we give an output to the MOSFETs from the Arduino that says switch on or switch off. And those MOSFETs switching on allows the relays to switch on. So that starts to drive our system.
Alright, so the control for the Arduino is actually just a big loop that repeats forever. So it continuously checks if the car is on, it'll check the temperature of the car, make sure that it's not getting above 90 degrees Fahrenheit. And if it does detect that, it'll start the system and either run for 30 minutes or until it detects that the temperature is below 50 degrees Fahrenheit. At that point, it will shut off, whichever one of those comes first. And then if the car is off, it will the system will stay off for 5 minutes just because there might be something like the car is stopping to just go to the gas station real quick. But then after that 5 minutes, the system will start up and do the same thing, except it'll always just run for 30 minutes if it's not shut off after 5 minutes of the car being off.
So we wanted to, once we got our system together, test to make sure that the calculations that we did before were relatively accurate. So we used 16 pounds of ice in a 20-minute test, and in that 10 minutes, the first 10 minutes of that, the temperature within the box reached about 5 degrees Celsius, which I think is about 40 degrees Fahrenheit. The temperature then slowly climbed back up to 6.4 degrees Celsius. You can see on this ambient temperature of the enclosure graph that it was approaching steady state. And then the initial water temp the difference between the initial water temp and the final water temp in the heat exchanger was about 2.7 degrees Celsius. And that had a similar effect where it started to reach a steady state value as the temperature of the water approached the temperature of the enclosure.
Alright, so with this steady state temperature, we used our equations from before to determine what would be the steady state temperature given our worst case scenario. And that was actually a temperature that was higher than the measure, what we calculated inside our box, which means that either our cooling system is delivering more cooling than we thought, or our box is protecting the system from more external heating than we originally planned for, which means that our system is doing better than we hoped at the beginning, and it is proves that it's viable. So the impact this has on all the public welfare and everything. So Michigan's infrastructure is based on natural gas. Roughly 80% of all the Michigan homes and everything is powered through natural gas. And if any of this methane gas ever leaks from any pipelines or anything like that, the greenhouse effect is way worse than CO2 or anything else like that. So it's very important for the system to be detecting the methane emissions. And with our cooling system added, it stops any more downtime that could have possibly arisen due to the system emergency shutting off and needing to be reset. So we're effectively lowering all the methane emissions that could be going into the environment.
So we just want to list a few future changes because this design is a prototype, so we want to just give a few recommendations for if consumer design wants to implement this in the future. So the first thing is to verify all the electrical circuits and components. We are not electrical engineers. We really, really did our research. We're confident in our design, but we're not so confident that we don't want an electrical engineer to look at it. So I know consumer design has a lot of electrical engineers, and so does Michigan State University, so assigning this task to one of them would be very helpful. And then on that same line, we want to move the prototype circuit to a PCB. Right now it's on just a solderless breadboard, so there's a lot of wire management that needs to go into it. If you move to a PCB, you can just like run it, place it, it'll be fine. And then we want to improve the stability of the system with the Caparo frame. We weren't able to get that much time with the car, but once the system is in the car, it's possible to just set up supports along the Caparo frame to make it just a little bit more stable during driving. And then just in the future, continuously monitor the system and adjust as needed. So if you decide, really we don't need this much cooling power, you can change the ice amount that you put in. If you decide you want it to run at a different time, you can change the program, just things like that. Yeah, so just to conclude, we want to thank you, Stephanie, and thanks to Consumers Energy, and thank you to Professor Wright for mentoring us through this process. And I'm going to load a program onto the Arduino, which will start the system running. And if any of you want to, you can come up and feel the cooling power. It'll be running for 5 minutes. Yeah, most coolers were saying they could keep ice around throughout the whole day. It's not clear if they need all of the ice, but as long as the water temperature is low enough, it should provide enough cooling.
And you think you overloaded, meaning going on the safe side as far as adding ice?
Yes, yeah, we were cooling this to almost freezing inside. So yeah, if any of you are interested, it's all running. So.